It's my great pleasure to present to you today one of our Google Tech Talks here in New York in person. It's been a while for me, for sure. I'm sure for others too. And it's quite a treat today. It's my honor to host Professor Mayur Naik from the University of Pennsylvania. He received his Ph.D. at Stanford in 2008. He then joined Intel Labs at Berkeley for a few years, became assistant professor at Georgia Tech till 2016, and then switched to Penn. He's been a thought leader on many state-of-the-art software engineering techniques. Today, his main research interest lies in the intersection of programming languages and machine learning. And so we have the pleasure today to listen to the perspective of where we are and what might come next. And with Mayur today, we actually have the pleasure to have two of his grad students here, Pardis and Aditya. So with that, please join me in welcoming all of them.
Thanks, Pranyu. It's a pleasure to be here. So today I will talk about our journey over the last 4 years since we began working on integrating machine learning into our developer assistants. This is joint work with my students who are both here, as Pranyu said, Pardis and Aditya, but also with folks at Google Brain, in particular Hanjun and Petros, who happens to be here. Okay, so the theme of my talk is based on this wonderful book by Daniel Kahneman in 2011, titled Thinking Fast and Slow. And it describes these two modes of human thought. He calls the first mode system 1, which is fast, that it operates automatically and quickly with little or no effort and no sense of voluntary control. And there are many examples of this mode of thinking that we use day to day. For example, adding 2 plus 2 or driving a car on an empty road and so on. But we also have this more deliberate and slower mode of thought, which he calls system 2. And examples of this mode include solving much more complex puzzles, or for example, parking in a tight parking space and so on. Right? And this dichotomy has become has attracted renewed attention in the age of modern AI. And when I was asked to give a high-level and long-term vision talk about developer assistants here today, I started researching the literature, and what I found was this striking dichotomy even in the space of developer assistants. Right? So what do these two kinds of developer assistants look like? Well, the ones based on system 2 use what is called symbolic reasoning, right? While the ones based on system 1 are based on deep neural network models. The system 2 based tools are written by human experts, while the system 1 based tools are trained on large corpuses of code. And system 2 based tools have been around pretty much as long as programming has been around, so since the 1970s, and continues to this day, whereas the system 1 based tools are much more recent. They have just been around since 2018. And here are some of the latest incarnations of these two kinds of developer assistants, which you might or might not have heard about. So for system 2, my personal favorite is this static analysis framework called SAML, which is now a part of GitHub. It began at the University of Oxford back in 2006, but was acquired by GitHub in 2019. And they have this declarative query language, which is similar to SQL for programming relational databases. And they call it CodeQL because the goal here is to query code rather than tabular data for SQL. And the remarkable thing about Semly is they have essentially democratized program analysis. So their hope is that end users will be able to build these symbolic reasoning checkers for their own purposes, ranging from everything involving, say, enforcing coding idioms within a company to finding complex security vulnerabilities. Okay. On the other hand, the latest incarnation that you might have heard about of System 1 based tools is GitHub and OpenAI's Copilot, whose goal is to complete a piece of code, right, based on the context that it currently sees. Okay. Now, what I'm going to do next is show you two prototypical tasks that I will use throughout this talk. Let's start again with System 2. These tools gained traction first in around 1998 when security became a big deal. So the most common kind of security attack that we see is what is called SQL injection. Even after 2 decades, it remains in the top 3 most common kinds of security vulnerabilities. Okay. And this is a task that you would want to solve using System 2 because it involves, as I will show shortly, a very complex series of steps. And even human experts who essentially find these kinds of bugs in production code have a level of ingenuity that you cannot get using System 1, at least today. On the other hand, the prototypical task that I like to talk about for System 1 is what is called detecting variable misuses. This was introduced in 2018 in a paper titled Learning to Represent Programs with Graphs. And I remember being distinctly and very pleasantly surprised by how one could even manage to formulate and check a problem like this. Because my entire career was spent with System 2 based tools. And we cannot even start to write the logical reasoning steps for catching these variable misuse bugs. And yet these are very common bugs, again, pretty much as old as programming itself. They typically arise when we copy a piece of code from one place to another and then forget to consistently rename variables. Right? And around 2018, this was incorporated into Visual Studio IntelliCode. Right? So in summary, what I've shown you here is 2 tasks that I feel are both equally important, yet one cannot even begin to think how to build a developer assistant for one of these tasks using a system that isn't currently used to solve that task. Okay. And so now the question becomes, there are many kinds of tasks we would like to solve. I have listed the ones that I'm familiar with. And many of these did not even exist until a few years ago. If you recall, System 1 based tools began arising in around 2018. And before that, we never thought, for example, to use to build developer assistants, for example, with tasks like program merging. I mean, these are tasks, again, which require a lot of human creativity, but yet we are not able to write a good set of logic rules to to describe or check them. And undoubtedly, this field is going to, this set of applications is going to keep growing as these systems become increasingly powerful. And so a natural question today is, which system should I use for my task, right? And what I'm going to convince you today is that you want to use both of these systems. It might not be in equal amounts, but it will almost certainly be the case that you will see that tools built using just one of these two paradigms end up hitting a wall. Okay, so let me begin first with challenges that System 2-based tools face. As I said, I've spent most of my career building these sorts of tools. Here is actually a real Python program. And here is a complex sequence of steps that show an SQL injection attack. So for those of you who are familiar with this, the technical term is taint tracking, right? There is an untrusted source, in this case, the function called report, which takes as input a request that an attacker can control. And then we can trace a sequence of flows in this program, potentially even going across files or projects until you eventually reach what is called a sensitive sink, right? And the goal of an attacker is to control the input to this program, to craft the input to this program so that there is something bad that happens when that input reaches this sensitive sink. Okay. Now, this kind of tool can be built using SAML today, using CodeQL. But there are many challenges. SAML is itself not a perfect system. And I'm going to give 4 of the main reasons why that is the case. So the very first reason is, in order to check something, you need to be able to specify that thing formally in logic, right? And I just gave the example of variable misuse errors. It will be incredibly complex to even specify the expected behavior, right? So specifications are tedious at best and vague and informal at worst. Even if you manage to formally write down specifications, that is the expected behavior of programs, there we have theoretical limitations. This goes back to the halting problem in computer science. What it simply means is you cannot build a tool that will be exact in terms of accepting or rejecting programs, as well as guaranteed to terminate, right? So you have to give up one of these 3 pillars, either have to be unsound, that means you can produce false negatives, or incomplete, which means you'll have to produce false positives, or you'll have to let the tool run potentially not terminate, right? But now let us say that you even manage to, you have formal specifications, and let us say you have abstracted the problem enough that it is now decidable. But then there's scalability issues, right? We have limited resources in the IDEs that we have and so on, that we have to make further trade-offs. And lastly, even if we manage to solve all of these problems, there are all sorts of real-world constraints, missing pieces of code. And this is something where we realize how good System 1-based tools are. They don't even need the program to compile or run, right? Whereas in order to apply a System 2-based tool, you need the program that you're checking to meet a lot of hard constraints before you can even get this tool to produce interesting results. So let me give some more concrete numbers here. We did this interesting experiment just a couple of days ago. We ran our taint tracking analysis from SEML on the top 20 most popular projects in Google's repository on GitHub, sorted by how much Python code they had. And this goes from 12,000 lines of code all the way to 2.5 million lines of code. And we ran around 21 queries. These are checkers that SEML engineers have written in CodeQL. I'll show one of these checkers later on today. And these checkers are known to be fairly accurate if only they could terminate in a reasonable amount of time. Right? So they're known to find high severity bugs. But what you start seeing here is it takes an extremely long amount of time, even on projects which are under 500,000 lines of code. And then the tool just stops running once you have more than 1 million lines of code. Okay. This, by the way, is not specific to taint tracking. I know of projects in other languages and analysis tasks other than the ones you see here, where you repeatedly see the same phenomenon, where you are faced with this hard trade-off that if you want your tool to run on large pieces of code, then you necessarily have to give up on accuracy, which in turn means that developers could be swamped with false alarms and stop using the tool. Or the tool is very accurate, but now it can only run on under 1 million lines of code. Right? So hopefully I've convinced you that there are interesting challenges to be solved for System 2-based tools, even for tasks where that is the right approach to use. Right? And so there's a role here for System 1-based ideas to address these problems. Okay. But my talk today is not going to be about that. And there's a lot of interesting work on using System 1-based ideas for improving System 2-based tools. What I'm instead going to do is look at this more recent and exciting space of tools that are based on System 1. And when these came around in about 4 years ago, even I wondered, is the game over, so to speak, right? That should we stop building System 2-based tools, right? You see this, by the way, in other fields of AI, in computer vision and natural language processing and so on. You cannot even imagine building tools that would use logic reasoning and so on, right? You get much better results simply by training larger and larger machine learning models on increasingly large data sets, right? But as I delve deeper into this space of tools using System 1, I realized that there were many challenges that were there. And many others also noticed this or were aware of it. But I hope to convince you today that there is actually a very good fit between the kinds of challenges that System 1 faces and the solutions that System 2 offers. Okay. Okay, so let's come back to our problem of detecting variable misuses that System 1 is supposedly good at, right? Now, what are the inputs and outputs of this problem? So the input is a piece of code, typically a single function, in this case, a Python function. And the output here is to pinpoint a location in the code, so the line and column number, and a replacement variable, right? So presumably the variable x1 there is misused, and so we should be using Y1, right? So this is sometimes called the software 2.0 programming stack. So this is presumably how many of the future systems, which I call System 1, will be built using. So there are 3 steps here. You collect a lot of training data, you feed it to a learning algorithm, and you learn a certain representation, okay, which is in the form of a deep neural network, right, which has inputs and outputs. For the task of variable misuse detection, the inputs are program text, in this case, a single function, and the output is these 2 pieces of information, so a location in the input program and what variable should be the one to use at that location. Okay. Now, the way this representation is learned is using an algorithm called stochastic gradient descent. And I'm not going to go into the details of this, but what is essentially happening here is we have to learn the parameters in the form of weights that allow us to best fit the training data, right? So the training data being in the form of pairs of input programs and output location variable pairs. Okay. Now, that raises an interesting question. How do we represent the model for code? Now, we know how to do this for images, right? So there was this groundbreaking result of using convolutional neural nets for representing images about a decade ago. We also know how to represent natural language text, right? And the state-of-the-art model is what is called a transformer. But that begs the question, what is the right representation for code, right? What I'm going to do next is tell you how 2 of these sub-problems need to be solved. The first one is, what parts of a program do we need to even represent, right? Because code is not as self-contained as an image or a piece of text. It can be connected through libraries to even other projects. In fact, you can even view the whole of GitHub as one giant knowledge graph or code base, right? And the second question is, once you have determined what information to capture, how to embed it in a high dimensional vector space. Okay. So I'm not going to go deep into the technical concepts here, but I'm going to give you a high level overview of the different representations and their pros and cons. So one can imagine that programs are simply like natural language text. They are a sequence of tokens, okay? And use transformer models that are popular for natural language processing. Now, the good thing about this is you can train these models on enormously large code corpuses using specialized architectures, so GPUs. But the downside is that they fail to capture rich semantic patterns in code. I'm going to show you later how these models on the surface seem very accurate, but as they attempt to solve longer range tasks, for example, completing large pieces of code, they will start making all sorts of mistakes, from simple parsing errors all the way to introducing security vulnerabilities. Okay. So another problem with them is they have a limited amount of memory. And so there is only so much of the entire programming ecosystem that they can look at a given point in time. Okay. On the other hand, we do know that to reason about program correctness, you typically have to look beyond just the one function or even the file that you are working on. So nevertheless, what you see here is as these models have grown bigger and bigger, so more and more parameters, the B there stands for billion. So as you go from top to down, you see the models are getting larger. And as you go from left to right, what we are doing here is giving the model more leeway in getting the right answer. One of the remarkable things about System 1 is that it can produce as many candidate answers as you want, unlike in System 2, where you have hard-coded the logic rules and it is not flexible enough to produce more than one candidate answer. And so that is how we get the k equals 1, 10, and 100. So you can allow these models to produce either one solution, 10 solutions, or 100 solutions. And as you give it more room to make mistakes, so you'll see as we go from the top right, top left, to the bottom right, the accuracy of this code completion task that we are looking at generally increases. Here, the human eval data set is a set of programming puzzles that humans wrote, because these models are so big that they were actually trained on the whole of GitHub, code forces, and all the other code corpuses out there. And so this paper, which talks about these results, is the Codex paper from OpenAI, which is the model underlying GitHub's Copilot developer assistant. What you see here is that on this human eval data set, not only did you have the solution, but you also had unit tests. So this actually is a pretty significant way to assess how good these models are doing. We are not looking just at blue scores or checking whether the programs produced are correctly parsed or have no static or don't have type checking errors and so on, but we are going all the way to checking semantic correctness, even if functional correctness, even if partially on some unit test cases. Okay. So in order to capture richer semantic information, one can then imagine that programs are not a sequence of tokens, but there is much richer graph-like structure here, right? So we can take the abstract syntax tree, which is the parse tree of the program, and we can augment it with additional edges that capture the flow of data and control. And we can use a different kind of model called a graph neural network. And in the early days of applying System 1, graph neural networks were very popular until around just a couple of years ago, when this remarkable paper by Alon and Yahav showed that graphs have this serious bottleneck problem. That as you train models to capture this rich semantic information in programs, they end up mostly learning the shape of the graph rather than how information is propagating over long ranges. And they even designed this synthetic graph benchmark where they had a knob called the problem radius, where as you go from 2 to 8, the graph becomes increasingly complex for a human to reason about. And they showed how different variations of graph neural networks dramatically drop in accuracy. So accuracy of 1 is the highest and 0 is the lowest. And this was a nice illustration of what all of us suspected was the problem with graph neural networks. Right. So I've shown you these two extremes, treating programs as flat text versus as a graph. Now let us see something in between these two extremes. Some of those same authors who found these limitations of graph neural networks came up with a different representation, which is, let us represent programs as a set of paths in the abstract syntax tree. So now I've shown you the tree representation of the program. If it has n nodes, then there is n square paths connecting every pair of nodes. And you can sample some of them because n square could be very large, right? And now you can embed this set of paths and use that as your representation of this program. And for a while, this seems to work quite well because it combines the benefits of both of these approaches. But as I will show later today, it is very easy to confuse even this model, which happens to be called code to seek. Okay, and I'll actually show how one can even systematically create attacks that often get this model to give you the answer that you want it to give rather than the actual expected answer. Okay, so these are called targeted attacks. Now, there's even more work here that tries to improve upon code to seek. This is called graph transformers. So the point here is, can we now combine transformers with the benefits that you get using graphs, which is capturing long-range dependencies. In fact, some of this work is done by folks at Google. And while these models are certainly more robust than the ones I've shown you before, they also have issues with increased complexity and decreased scalability. Right? They can, for example, it might be easy to encode a few kinds of semantic relations, but beyond a point, it can become very challenging to engineer. Okay, so now that I've given you a high-level overview of where we are today with System 1-based tools, let me talk about 3 challenges and what work is being done using System 2-based ideas to address those challenges. So if you're even going to use this approach to, say, build a developer assistant, the very first thing you are faced with is collecting a lot of data. And while this has revolutionized System 1-based tools in other domains of AI, like natural language processing and vision, simply by crowdsourcing these tasks to regular humans. Okay, you have heard about the visual genome from Stanford, the habitat data set from Meta, and so on. This is just not something that can scale for programming. You cannot get a lot of programmers to label things for you. Many have tried, and I'll show you some of the pitfalls that one should be concerned about. There's also the problem with getting System 1 to produce correct results, right? Even if your input data is perfect, there is a stochastic aspect to these systems that will prevent them from always giving certain formal guarantees that System 2 can give. And then I'll talk about the third, which is, even if, let us say, we have a perfect input data and we manage to produce highly accurate results on data within the distribution that the model was trained on, it is easy to fool these models on what is called out-of-distribution data, right? And I'll call this the generalizability or robustness challenge. Okay, others have called this distribution shift. Okay. So what I'm going to do next is show you examples of each of these challenges and suggest solution strategies. Okay, so it will be a whirlwind tour of examples and ways to overcome these challenges. So let's start with data quality. So what does high quality data even mean? So I believe it means these four things. First of all, you need a lot of data, right? But you also need data that covers all cases, right? So it has good coverage. But now there are these competing problems, which is you want to have less noise in your data. For example, let's look at the variable misuse detection problem. If you simply used data from, say, GitHub open source projects, there is likely to be noise there, which is programmers make these mistakes themselves. And so now your data set will have those mistakes as well. Right? So that would be noise. There's also the issue of bias. So you might have, for example, a highly imbalanced data set, or you might have a data set that is not representative of the final the instances that your model will see at test time, okay, or in deployment. So one of my favorite papers in this field is by Miltos Alamanis, who showed in 2019 that if you naively mine a large code corpus, then there's actually a lot of duplicates, which we all knew about. But what Miltos showed was he actually quantified how much various accuracy metrics of System 1 based tools would drop if you cleaned this data, right? And what you see here is there are 4 different tasks I've shown you, going all the way from method naming to variable naming, code auto-completion, and docstring prediction, using a variety of different models, such as code to vec, seek to seek, and so on, and using a variety of different accuracy metrics, right? And what he showed was that if you removed what are called these cross-set duplicates, so at test time, you won't have any samples that overlapped with what the model saw at training time, which is a fair assumption, right? So you don't want the model to memorize things and regurgitate them. Then what he saw is the difference is shown in the third column, that the accuracy of these models dropped significantly, all the way up to 41.6%. Right? So at least I found this result to be very surprising. And even as I tell you these challenges, you can actually see System 2 based tools at play. In order to even clean data, you will use the kinds of tools that we have built over the years with System 2. But as a solution strategy, I'm going to propose that we can use those tools to even generate data. Okay, so but let us say that we have cleaned our data, we have deduplicated it. Is it now safe to use it? In our own work this year, which appeared at ICLR, called Code Trek, we started out with this synthetic data set. So again, we are looking at variable misuse detection in Python. We started out with real programs that are written by humans, but we said, let us replace each variable with other candidate variables in scope, and now we have both positive and negative samples of variable misuses, right? For example, if we replace that y1 with another variable in scope that type checks, let's say x1. Now we have a sample, a synthetic sample of a variable misuse. Okay. We trained 5 existing models on 700,000 instances of such data from GitHub. And then we tested this model once on samples in the same distribution, that is what is the synthetic data set, so 378,000 instances. But then also on a few real-world instances from GitHub commits. And this massive difference in the test set size, so 378,000 versus just 398, that's not a typo there, that shows you how hard it is if you want to crowdsource the collection of this data, right? So people have tried mining GitHub commit logs and so on, but it is a very noisy process. And so we managed to have this highly curated set of 398 real misuses that programmers had committed, as opposed to these synthetically generated ones. Right? And what we noticed was that across the board, different models that I've talked about, including our own, which I'll talk about later in the talk, CodeTrek, the accuracy consistently drops. And the reason I like this example is, even as someone like me who has a lot of experience working in System 2, I was at first discouraged looking at results like the ones you see with Great and QBERT, which seem to imply that this is almost a solved problem, right? Showing an accuracy of well above, of close to 90%. You wonder if I should even be working on this problem because you have only so much room for error. And I've noticed this consistently, not just in the space of developer assistant tools, but also in natural language processing and computer vision, where you see a lot of research papers giving the impression that these are solved problems. But the moment you apply them to instances out of the distribution, you start seeing a dramatic drop in accuracy. Okay. There are a lot more details in this work where you can understand why some drop much more than others. Okay. So for example, CodeTrek, even though our work wasn't actually the best performing on synthetic data, so we have around 70% accuracy, which is not the highest, but the moment we use these out of distribution samples, and our model turns out to be more robust and ends up actually being the highest accuracy among the ones that we see here. So I then wondered, what can we do to get better quality data? And this is where I'm going to show you how System 2 can be used. So instead of asking humans to label data, as we have done in other domains like vision and NLP, or even using data that is coming from, say, code corpuses out there that we then synthetically manipulate, one can ask, can we chain together the various tools we have built to generate new data or to clean up existing data? And here are all the kinds of tools that we have. Okay? And in recent work, what we managed to do was even generate a data set of programs and their intended specifications. Okay? So this, I believe, is the first executable large-scale data set that exists out there, which humans would have a very hard time writing preconditions. They're a kind of specification for real-world programs, right? But by chaining together what is called a regression test generator with what is called a program reducer, you can actually get very high-quality data, right? So I think this is a very promising venue for future work. As another example, you can use tools like fuzzers. The problem of checking whether a line of code is reachable on some input is very hard for System 2 to solve. But if a fuzzer reaches a line of code, right there you have a sample if you want to train a machine learning model for checking reachability. Right? In the interest of time, I am going to go a bit faster here. Let's now talk about the output challenge. Even if you had solved the problem of getting good, high quality input data. So what you see here is models like GitHub's Copilot for code completion or Facebook's transcoder for program migration are not just injecting errors. In the case of transcoder, you cannot call the pow function on an integer, right? So you have to do math.pow a comma b. But you can see Copilot even injecting security vulnerabilities into code. Okay. So one of the ways you can use System 2 is to simply check the results on some test suite, right? That itself is a good use of System 2 to improve System 1. Okay. But this only goes so far. You see here alpha code. At first, you are impressed that it can solve very complex programming puzzles. But then you realize that it has to produce, for example, 100,000 candidate answers, run them, well, cluster them in some form, and then run them on unit tests, and then pick the 10 best out of those to feed to hidden tests. Right? And only then they manage to get the accuracy numbers that you see here. But this is just not sustainable, right? And this is happening today everywhere. So these are models from OpenAI and from Google. You see they produce a large number of candidates and then use unit testing to reduce the errors. The last thing I'm going to talk about, I'm going to skip a lot of this, and I'll be happy to talk offline about this. But I want to highlight just one piece of work by others. So let us say we have high quality input data and we produce accurate results at test time on samples that are in distribution. How can we improve generalizability? So this paper appearing last year is again one of my favorite. What it showed was that System 1 based tools were using these very weak metrics for measuring accuracy, like blue scores and how often parsing checks were successful. But they then used various static checkers. So these could be potentially viewed as code QL queries, and actually showed that, especially for long-range code completion, models such as Codex and CodeGPT, even though they seem superficially correct because the code they produce parses, they actually ended up failing many of the semantic checks. Right? And so they came up with this idea of leveraging System 2 to improve the generalizability or robustness of System 1. And the idea turns out to be remarkably simple. All they're saying is, given an input context, which could be code along with comments and so on, and the goal is to fill in a hole, say a missing function. The idea here is that instead of simply training these models on pairs of this context and program, if you were to use additional information that you obtained from static analysis, and the way you might get that is, as you parse this context, you might learn, for example, which variables are in scope, and that will guide at each step of generating that program this eventual model that we are building, so that it is highly unlikely to make those mistakes. Okay, so I've explained this at a very high level here, but I hope you can sort of get a sense of how Codex was doing it before, which is it has no idea about semantic properties of code, right? It is essentially just memorizing the context, program pairs, and therefore making all of these semantic mistakes. But the moment you integrate a static analyzer at training time, that is when you get significantly better accuracy results. Okay? There are many other ideas out here. Contrastive learning is another, which is at training time. With each program that you're feeding to the model, you also feed other similar programs, but also dissimilar programs that you want the model to discriminate. And all of these are fairly straightforward to do using system 2 based tools. Okay, so we have transformations that are semantics preserving, we have transformations that produce different semantics, and so on. Okay, so now I will conclude. So we know that today's developer assistants follow this dichotomy, which is they're either based on system 1 or system 2. But both of them have problems, even if you use them for problems that seem well suited to solve using that system. So system 2 is here to stay. It has proven its capabilities, at least as far as I'm aware. No deep neural model has found a serious security bug, whereas this is very routine for system 2 based tools. So for example, fuzzers and so on that Franio's group here has built have found a lot of high quality errors. And if you talk to folks from SEML, they have no interest in building tools that find low quality, low value bugs, including most bar misuses. Okay. But they also face these hard challenges, right? On the other hand, system 1 came to the forefront to address these challenges in system 2, but they themselves have their own problems. But what I believe is, and I hope I've convinced you at least through the few examples I was able to show, that there is a lot of room, and this kind of work is already happening for how to use system 2 to improve system 1. Okay? And what I didn't talk about today is how system 1 can be used to improve system 2, for example, building neural fuzzers and so on. Okay. So with that, thank you for your attention, and I'll be happy to take any questions.
Well, thank you. We can start with live questions first. Dan, can you hear me?
Yeah. Hi, thanks for the great talk. I agree with your point that system 1 and system 2 are very different, but leveraging system 2 to improve system 1 techniques, like generating high quality code, improving correctness, are great ideas. I had 2 questions, so we could take turns if others have questions as well. One high level question is, one thing I've learned about practicing ML in this learning for code space is that model metrics like accuracy aren't the only factor towards usefulness. So even for models that are unconfident or biased, they can still be used in ways and designed in tools that are safe if designed correctly. So you may have a biased or insecure generative model, but if you use it only for re-ranking purposes for some existing semantic engine, then it's still safe. So curious if you have any thoughts about how to use system 1 tools in ways that are kind of safe, despite potential lack of provable security.
No, I think this is an open question, right? It's a great point that you raise. I think that there's a bigger problem here that we are actually solving in a different project on how can you close the loop in system 1. So let's look at Google Scholar, a tool that Google has built, right? You notice some mistake there. What do? Okay, so you cannot, well, you can correct it and it will make this hard change, but it is not going to feed this back into the model. At least that's my understanding, right? So I think this is a much harder and interesting question. I'm actually even more interested in this problem in the medical domain. We are working actually with cardiologists and neurologists and so on, where the models are actually being used on humans but then if they make mistakes, how can you recover from them and improve the model over time? So there's work on provenance tracking and so on from database research that we are looking at to to improve these models. But yeah, that's the best answer I can give you at the moment.
Do you want to go with your second question?
Cool. Thank you for the answer. My second question is about data quality generally, which you talked about on slides 18 and 19, if you'd like to go back there. I don't know if you've thought about this specifically, but the invention of BERT introduces the pre-training and fine-tuning sort of regime for training models that can be applied to learning for code as well. And my question is about different dimensions to data quality and their usefulness in pre-training and transfer. So there are a few different methodologies for generating good pre-training data. For example, if we want to use System 2 to produce better quality data for System 1 technologies, maybe one flavor is general self-supervision for general knowledge, things like QBERT or span denoising, where it's just learning general knowledge about code. Another one is maybe more transfer-oriented, so focusing on pre-training tasks that are most similar to the downstream tasks that people care about for tools. And maybe a third one is sort of multimodality, so focusing on or trying to use a bunch of different tasks and pre-training, a wide variety, maybe involving both natural language and code to have sort of task augmentation. So curious if you have any thoughts about, good pre-training strategies.
Yeah, unfortunately, I don't work in this space. So as I said, my specialty is in System 2. So I think, folks at Google actually will be at a better position to answer questions about pre-training. Yeah, sorry, I'm not. I don't think I have a good answer.
Yeah, that makes sense. I guess the approaches you've presented are about generating high quality data using System 2. So this is specific to downstream tasks.
Yeah, and I feel, I just very cursorily mentioned it. I think there is a lot of room, to what I say, chain together these tools. Even just within Google, there will be so many compilers and fuzzers and decompilers and so on, right? I was just wondering, even if Meta were to build transcoder differently, right, to say go from Python to Java, they could reduce both of these to a common intermediate representation, maybe LLVM IR, right? And you can chain together all of these tools, and in a while, even though these tools themselves are imperfect because these are undecidable problems, but you chain them together and you get formal guarantees on the data that you generate. So I'm quite excited about this space, but it is so new that I have not applied it beyond just some of the problems that I'm showing you right here. Okay.
So I know we're nearly out of time, so if people need to drop, we understand, but we have a few more questions on Dory as well, so I keep asking. So who wants to stay is welcome to stay. Any questions in the room? While you're thinking, you can ask, have you seen any interesting ideas on using System 1 type tools to address scalability and precision issues of System 2 type tools?
It's a great question. I mean, the only one I'm aware of is neural fuzzers. I mean, work which I believe even Google's OSS fuzz uses occasionally. Do either of you know? Yeah. Yes, I mean, this is work we are doing now. I think it is less exciting to the general public because, the System 2 is perceived as more sort of conventional. And so if you use machine learning to just improve them incrementally, it's not considered as flashy as if you used System 1 and improved it a bit with System 2. It is our goal, though. In fact, the students I have here are excited about actually using the ideas that I described to maybe find the first security vulnerability using by using System 1 to help scale System 2. Many of these code QL queries I showed you don't even run on large projects, but if you could only make them run using ideas from system one, for example, to predict very selective data flows across files or projects, then you could presumably find new vulnerabilities. Okay.
You mentioned that System 1 tools give you lots of answers, like one of the advantages, right? That you can generate more than one candidate. How do we effectively show this to the developer, right? In the end, we have a developer on the other end that now probably doesn't want to look at 100,000 solutions, right? How do we maybe pick a few, and how do we even show multiple of the same problem?
Yeah, I haven't thought about this. It's a great question. Does either of you want to answer this?
So one of the approaches that people have tried is writing unit tests or generating unit tests, which is not a good solution because having unit tests for every one of those different programs is very difficult. So yeah, there is not any other thing that I'm aware of.
Yeah. So one of the things that I'm more interested in is, is actually generating specifications or tests automatically, because I think it's much easier for developers to see the results of tests, because they give you a concrete execution that you can, approve or disapprove of, as opposed to having to stare at each solution candidate piece of code and deciding which one is the best. There are many other ideas. You can even use, you can convert code to natural language. So you can, give extra information that this is what this piece of code is most likely saying. So I think this whole space is just getting started, right? I don't know the answers to many of these questions, but if you delve into it for a while, you actually start seeing a lot of interesting possibilities. Okay.
So you mentioned like some of the cons with the transformer-based models is that they don't do long-range reasoning, right? One of the advantages that I think we've seen is that they are fast, right? Yeah. Like if I'm in an IDE use case, right, the speed is quite important, right? Like how do you, are there things that we could, what are the things that we could add that will give us more long-range sensing, but still in an IDE use case?
It's a great point, right? So I for example, would love to see a problem like, the one that Google Bouncer is solving when a new Android app comes on the Play Store, clearly won't fit in the memory of a transformer, but what parts of it are the most relevant? What is it that a human analyst looks at? Clearly, they're not looking at the entire program. And I think you raise this interesting point, which is a transformer is just a sequence-to-sequence model. It doesn't actually have to be lexical tokens in the program. So we have thoughts about maybe running these system 2 tools to compute interprocedural summaries and this information flow that I showed you, and maybe embedding those pieces of information, right? So for example, the results of taint tracking. So you would still use the transformer model, but the thing that you would feed in is not the lexical tokens of the program, but this derived information that is coming from system 2 tools.
There's actually a question that came in about this. Right, system 2 creates a lot of intermediate representations, points to graphs or inferred derived facts of things, right? Is how much can we utilize that for system 1, and how important is the feedback loop between system 1 and system 2?
I think, again, this is all speculation. I think there's a lot of value, and we are actually working on these sorts of problems right now. I don't have good answers, but definitely I think you cannot expect system 1 to learn these complex relationships just by scaling. Um, um, Regarding the feedback loop, I mean, there's so many other architectures that I haven't talked about, like reinforcement learning and so on, where one could have more interesting interplay between the two systems. Okay.
There's a lot of question along those lines too. Do you have any sense, or I don't know if this is super relevant either, but do you have any sense of how like more languages with more rich type systems would fit into this mix? In some ways, I always see, like, I come from a system 2 background myself, so I always see these sort of like richly typed languages, like there's a lot of French ones, and or like Rust. I guess is like a more popular example. Rust doesn't have as many rich features that you'd see in something like Hawk, with like dependent types. But I wonder how that. So I always see those as sort of like a parallel part of System 2. It's sort of like you don't need System 2 if you can write a complicated dependent type program that verifies that it has these properties from the get-go. So I wonder, do you have any ideas of how that plays into this in terms of like?
So the reason System 1 is even so popular, right, is increasingly the shift in programming has been towards these dynamically typed, scripting languages and so on. So there's Python, JavaScript, and these are the two most popular out there. And that is where actually System 2 has very little to contribute because, there's no type information, as you said. Most of our tools actually, don't even, there are not that many static analysis tools, even for JavaScript and Python. It is extremely hard to build them. So definitely, but that's a trade-off, right? That, if programmers are going to use these languages for rapid prototyping, then, you have to go with that. So certainly richer types would be better. But if that is not what programmers are using, then one has to work around and figure out how to get these ideas working for untyped programs. Okay.
Go with two more questions. One came in here, which is program synthesis also seems to combine System 1 and System 2 style approaches. Is there common ground that we can build on for these systems?
Yes, of course. I think, in fact, this work that I showed you some time ago, NSG, is actually using ideas from program synthesis, right? So definitely there's a lot of this is the work I was talking about. So yes, there would be a lot of, I think, interplay. You see this even in robust fill. I think this is one of Google's works on spreadsheet programming, which is an example where the two are combined.
And then I'll go with my last question, which was on slide 7. You said you analyzed 20. You analyzed Google's GitHub projects with 20 queries. So what did you find? Which bugs do we need to fix?
Pardis, can you answer that?
It's a really good question. After I look at them and see how valuable they are, I will let you know.
Yes.
We are actually doing research on this right now, so you will hear from us if we find something.
Let us know for sure.
The problem with false positives is real. So many of the ones that I found you can't even exploit them.
Yeah, my experience with building these tools is that the first bug takes an enormous amount of time, but then there's a slow trickle and then there's an avalanche. Last year we built one of these tools which used actually System 1 to help System 2. This appeared in IEEE SNP, I think 2021. We found 400 bugs in the Linux kernel. And in the beginning, we were so discouraged that we actually abandoned looking at the Linux kernel after a month because this is very well tested code, and went back to very sparingly used Debian packages. But the moment we found bugs in those and came back to the Linux kernel, that is when we found an avalanche of bugs. So who knows? Maybe in Google's projects, it will be a while until we find them, but we might be lucky and find more over time. So
let me know, let us know. We'll definitely want to hear about your analysis. So with that, thank you. I know we went 10 minutes over. Thanks everybody for the patience. And thank you one more time.
Thank you.